My name is Karl Wust, and I will be presenting TLS-N, which is an extension for TLS to provide non-repudiation, which enables forwarding information about the TLS session verifiably to third parties. This is joint work with Hubert Ritzdorf, Gervais, Guillaume, Felley, and Srdjan Capkun. So let's start with TLS. TLS is a protocol that most of you probably use every day. And so if Alice wants to connect to some server, she can actually do this securely with TLS. She can verify the identity of the server using the TLS certificate and exchange some keys. And from that point on, her connection will be encrypted and authenticated with the server. Now, if Alice wants to forward some information from that TLS session to Bob, she can do so, but Bob has no way of verifying that this information that he gets actually originated from a session with the server, because Alice could just forge all of the messages since she has the symmetric keys that were used to authenticate the session. Now, why would we even want to do this? So one of the possible use cases is web archives, such as the Internet Archive or Google Cache. If we are able to forward such content verifiably, then these web archives could prove to their users that the content they provide actually originated from the domain that they're claiming it came from. Another use case, which is quite prominent at the moment, is blockchains. So how can we get reliable data into the blockchain? And this is something that Ari Jules talked about in the keynote. And currently, if we want to get some information about the world into the blockchain, we need to rely on some blockchain oracles that get data about the world, usually from some website that provides this data and that is trusted. And then that oracle pushes that data into the blockchain. But it would be nice if we could do this without this additional intermediary that kind of adds additional trust assumptions. So if we could do this without this centralized kind of oracle. So for example, I'll take the same example as from the keynote with the flight insurance. If we have a flight insurance contract where we have an insurance provider and a customer, and let's say the flight is delayed, so the customer issues a claim to the flight insurance contract, then we could say the insurance provider can tell the contract whether it's okay, or we can have some timeout, and then the flight insurance contract can pay the money to the customer. This is fine as long as the insurance provider is honest, but in that case, if we assume that he's always honest, we don't really need a smart contract. We can just trust the insurance provider to pay out the claim, which is kind of what current insurances do. So if he's dishonest, there's no way for the flight insurance contract to know whether or not they should do the payout, which means that nothing will happen. However, in this case, we have some reliable source of truth, which is the airline website, which will provide reliable data about whether a flight was delayed or canceled. So the idea is now, how do we get the data from this website into the flight insurance contract without needing to trust another third party? So our contributions are, we provide the first secure TLS extension that provides non-repudiation. This TLS extension can be used as a decentralized blockchain oracle, so any client that connects to a website can use this to basically act as a blockchain oracle for the contracts that they want to execute. We provide an implementation using the Mozilla NSS library, and we also provide an Ethereum library for Solidity for verification of TLS-N proofs. So to give you a high-level overview for how non-repudiation for TLS looks, so we have the standard setup from TLS. We have a certificate authority that verifies the identity of the server. We have a client that has a conversation over TLS with the server. And now we also have a third party, which is the verifier. And this can be a contract on the blockchain. And this verifier necessarily also trusts the CA to verify the identity correctly. And in the case of a blockchain smart contract, we at least have some trust to the server to provide reliable data. And that third-party verifier wants to learn about the conversation that was happening between the client and the server. Now, the server can provide some evidence to the client, which the client can then use together with the plain text from the TLS session to create a proof that he can then submit to the verifier. The verifier can verify these proofs and thus verifiably learns about the contents of the conversation between the client and the server. Now, if we look at a standard TLS session, we will start with the TLS handshake, and then there will be some requests and responses from the higher level protocol, for example, HTTP. And this is kind of how the normal TLS session looks like. What we add now is some steady processing on the server side. So the server will take the records that he sends and receives, immediately process them, and keep only very small state to generate evidence that he later provides to the client. So this means the server doesn't have to keep track of the whole TLS session, but only needs to store some few values. The client, on the other side, saves all of the plaintext TLS records, and he also saves the negotiated parameters from the handshake. Then at some point, the client will send a message, return evidence to the server, at which point the server will sign the generated evidence with his TLS private key and return the evidence to the client. The client can now use the plaintext records together with this evidence to generate a proof. And we also allow the client to provide privacy settings. So the client will be able to actually censor the proof. This is necessary because in many protocols, for example, HTTP, if you connect to an API, you will have some API token. Maybe you will have some passwords. So there's privacy-sensitive data that you don't necessarily want to share with third parties or even publish on the blockchain. Now, how does this look in detail? So we allow for two different levels of privacy protection. This is the more fine-grained version. The less fine-grained version you can read about in the paper. So when the server processes a record, he cuts it up into chunks in this case. So the chunk size is a parameter that's negotiated in the handshake. This could be, for example, 16 bytes. And so the server cuts up the records into chunks and creates commitments for each of these chunks of the record. And for these commitments, he will first create the so-called salt tree, for which he uses the TLS traffic secret and the record nonce as inputs to an expansion function that's already present in TLS to create the salt secret. And this salt secret is then expanded further to create enough salts for the commitments for the record. And the commitments of the record are then hashed together in a Merkle tree, and the Merkle root of this record is then included in a hash chain of all of the records of the session. And this means that the only thing that the server basically has to keep track of is the current value of the hash chain. We also, to each record, add an originator bit into the Merkle root, which basically says whether the record originated from the client or the server. And the server has to keep track of which record was received by from the client and which record he sent. So this is basically 1 bit per record, because in TLS, the records have an order for each respective sender, but there's no total order for the interleaving of the sending of the records. Okay, so now how can the client use this to censor the plaintext data? So let's say the client wants to fully discard record number 2, he wants to fully include record number 1, and he wants to include some parts of record 0 in the proof. This means that now for the last record, for record number 2, he can simply include the root of the Merkle tree in the proof and doesn't need to include any other values. He doesn't include any of the plain text. He doesn't include the salt secret. But this value is enough to reconstruct the hash chain given all of the other values, but doesn't leak any information about the plain text. For record number 1 that he fully wants to include, he includes the whole plain text, and he also includes the salt secret, which allows a verifier to regenerate the full salt tree, so to get all of the salt values for the commitments. With that, he can again regenerate the Merkle tree, get the value for the Merkle root, which he can include in the hash chain. For record 0, the client simply includes some of the intermediate values. So you can see them here. So for consecutive chunks in the record that he wants to include, he basically includes an intermediate value in the salt tree, which allows the generation of the salts corresponding to those chunks. And for chunks that he doesn't want to include, he simply includes in the proof an intermediate value in the Merkle tree, which allows the recomputation of the full Merkle tree given the other values. And with that, a verifier can recompute all of the required values for the hash chain, then get the value for HCN-1, which is the final value, final output of the hash chain, which is part of the data that the server signs. So then he can verify the signature from the server. Now let's go back to our flight insurance example. So in the case where the insurance provider is honest, we basically have the same thing as before. The customer issues a claim. The insurance provider is OK with that claim. The customer gets the payout. If the insurance provider is malicious, the customer issues a claim. The insurance provider says, no, this claim is not valid. In that case, the customer connects to the airline website in a TLS session using TLS-N. He will get evidence from that website, create a proof, submit that proof to the flight insurance contract. The flight insurance contract will verify the contents of that session, and if the contents check out, he will provide the payout to the customer. All right, so to summarize, we've provided a TLS extension for non-repudiation that is privacy preserving. However, redactions that are done by the client are visible to verifiers. This means that the client cannot simply cut out chunks of the plain text without this being visible. And our solution is efficient. And last but not least, this extension basically acts as a decentralized blockchain oracle that can be used by anyone to provide verifiable data to smart contracts so that they can act on real-world data. You can try this out. We have a website, TLS-N.org. Please check it out. There you can try out some interactive proof generation. So the extension is running on our website. You can also use the website as proxy for other websites. However, this, of course, means that our website in that case is an in-between trusted third party, so this is not intended for real use. We have code for the TLS extension available. As I've said, this is implemented for the NSS library. We're currently also in the process of implementing this for OpenSSL. We also have a smart contract library for Ethereum, and we have an example contract. So thank you for listening. I'm now open to questions. Yeah, so the question was whether we support things like session resumption, and the answer is currently not. So this is something that we've thought about, but this offers the possibility for some other attacks possibly. So there are issues with previous ideas for TLS extensions that offer this functionality that allow content reordering, that allow excluding some of the content. So this is one of the issues why we wanted to have the redactions visible. If you allow session resumptions, then you could basically jump in the middle of a session without it being visible that you already had some communication beforehand.
Thank you. Other questions? I have a very good question. So in slide 12, you mentioned that our solution is efficient, but I'm not really
Yeah. Yeah, that's also a good question. So we have some evaluation here as well. So the overhead depends on the level of granularity that we want for privacy protection, basically. So at the bottom, you can see record level privacy protection, which means that you can censor full records, but you cannot censor chunks of the record. And you can see that this is basically no overhead at all. And then depending on the chunk sizes that you use, the overhead increases a bit. So at the bottom, you can see the length of the records. 16 kilobytes is the maximum record length that is supported in NSS. I'm not sure if it's also the maximum in OpenSSL. And so for example, for 64-byte chunks with the largest size of records, this is just 2 milliseconds of overhead. And please keep in mind, this is also not optimized code. So this is so this can definitely be further optimized by parallelization and so on.